Today I'll talk about consciousness and the interface theory of perception. 1/3 of your brain's cortex is engaged in vision. When you simply open your eyes and look around, you're using billions of neurons and trillions of synapses just to see the world in this room. This might be a bit surprising to most of us because to the extent that we think about vision at all, we think of it as like a camera. Vision is just a process of taking a snapshot of a world that exists out there that has objects, colors, shapes, and motions. So there is a part of vision that is like a camera, and that is the eye. The eye has a lens which focuses an image on the back of the eye where there's a piece of tissue called the retina, about 120 million photoreceptors and 200 million interneurons that do sophisticated processing, a very, very sophisticated piece of computational hardware. It's also an example of unintelligent design. The light goes through the lens, and it has to go through all the interneurons and blood vessels before it reaches the photoreceptors, which are behind. That's really bad design. That's true of vertebrate eyes. It's not true of cephalopod eyes. They have it right. The photoreceptors are in front, the interneurons and the blood vessels are behind. We got the B model. So why all this horsepower in the brain just to look? The idea from cognitive neuroscience is that perception, vision, is really a reality engine. In real time, you're creating all the depths, colors, motions, shapes, textures, and objects that you see. So you are creating the reality that you experience right now. You're not just taking a snapshot of a world that was already there. So for example, just a couple concrete examples, this table and that table have exactly the same shape of the tabletop. One might look long and thin, the other short and fat, but they're exactly the same shape. Your visual system has rules for creating 3D shapes, and we understand those rules, and they force you to see things, in this case, incorrectly. And I know you probably don't believe me on this. You're welcome to come up some other time afterwards and measure them on my screen. They're exactly the same shapes. See if this works. The top and the bottom probably look very, very different shades of gray, the top and the bottom. But they're exactly the same shades of gray, and you can prove it with your own finger. Close one eye, put your finger over the boundary between the top and the bottom, and you'll see they're the same shade of gray. So you have a magic finger. So even your perception of shades of gray is a construction. You're constructing that reality in real time. It's a perceptual reality. It's not an objective reality. You see the 3D shapes. You see the shades of gray that you create. You probably see a cube floating in front of disks. In fact, the cube that you see is entirely your hallucination. All I've done is put little disks with cutouts, and you notice that your visual system notices that these cutouts line up, and so you actually hallucinate the glowing, you probably see a glowing line across. That's you're hallucinating that, and then you hallucinate the 3D cube that you see, and you probably see that it can flip, the cube can flip back and forth. How many get the cube flipping? Okay, so what that shows is that you first hallucinate the lines, then you build a new hallucination on top of that of a 3D shape, and then you notice you can build two of those, so you flip back and forth between the two. And to prove that you're creating the 3D, the glow of the lines, think of the disks as holes in a sheet of paper. You're looking through the holes, and behind you see a cube. How many get that to happen? Notice when you get that to happen, the glow stops. Do you notice that? So that proves that you create the glowing lines and you turn them off when you decide to put the cube behind. Your visual system is creating the lines, is putting the glow, it's all you. It's not there on the screen. You create all the colors that you see. Light has no color. If you asked a physicist, does light have color? They'd say no, it has frequency, wavelength, but not color. That square and that square. That one and that one. Same color or different? You know the answer is supposed to be that they're the same. They're actually identical inks. And I'm just going to remove some context. Put it back. I'll go back again. Watch the yellow one turn brown. Now watch it ramp back up to yellow. You're actually seeing your own visual system change the color in real time. You're computing that color in real time. One more time. This is a lot of fun. Right? So there it is. It's yellow. Watch it change to brown. You're actually seeing your creative powers in action. Then it goes back to yellow. It turns the glow back on. So that's all you. Yeah, this is all no drugs. That's great. So you create everything that you see, but your visual consciousness is different than you might think. On this demonstration, both screens, I'll show you one picture, a blank screen, and then the same picture, but there's something different. There's something that's been changed. Can you find it? I'll give you just 1 second to try to find it. Yeah, if you might let other people have a chance first. So there's a boat back here that appears and disappears. I'll give you another chance here. So maybe just raise your hand when you know it. Aha. This one's a little more tricky. So this one took me about a minute. By the way, there's no correlation between the IQ and the time it takes to... So you don't want to leave home without this. It's the engine on both sides. So notice that you see less. You're not a camera. You're not taking a picture of the whole scene. You're creating, but you only create where you really attend. One more chance, real quick one. Just raise your hand if you get it. A couple, okay. Notice the bar behind them going up and down. So notice that after you know what it is, you can't help but see it. But before, you were blind to it. Quite striking. So vision is a constructive process. What I've told you so far is all standard. What's also standard in cognitive neuroscience is the idea that perception is reconstruction. The argument is an evolutionary argument. Those of our ancestors that saw the world more truly were at a fitness advantage compared to those who didn't. And so we are the offspring. The ones that saw more truly had a better chance of having kids and surviving. And so we are the offspring of those who saw more truly. So our perceptions, although they're constructions, are in fact reconstructions of the truth of the 3D world out there. That's the standard story in cognitive neuroscience. Perception estimates true properties of the physical world. Evolution guarantees that these estimates are accurate, and perception is therefore generally veridical, which is a fancy name for true. This is the standard story, and I think it's completely bogus. It misunderstands evolution completely. In my lab, we've been doing studies of evolution using mathematical models called evolutionary game theory and genetic algorithms, where you can actually create perceptual strategies. You can create any world that you want in the computer, in fact, millions of them at random. You create perceptual strategies for organisms competing in those worlds. Some of the organisms see all the truth of that world. You play God in this world, so you say they will have all the truth in their perceptions. And others are only tuned to fitness. And you have them compete, and you penalize them for costs, for the time it takes to get their perceptions, the information costs, computational costs. And the bottom line is, in these competitions, in world after world, truth goes extinct. It's not the most fit strategy. And instead, something that I'll call an interface strategy, and I'll tell you what that is, that's just tuned to fitness, drives truth to extinction all the time. And when we do genetic algorithms, truth doesn't even come on the stage. It never evolves. So in evolutionary games, we put truth on the stage and it dies. In genetic algorithm, it never gets on the stage. So this has led me to think about perception in a different way. If perceptions have not evolved to be true, how can they be useful? I mean, how can our perceptions, we usually think of perceptions as being useful because they're true. They're telling us about the truth of the world. So I think a helpful metaphor is the desktop interface on your computer. Your desktop has nice little graphics like this blue rectangular, I don't think I can get, you see the blue rectangular file icon there, right? So that icon is blue, rectangular, and in the lower right-hand corner of the screen. Does that mean that the file itself in the computer is blue, rectangular, or in the lower right-hand corner of the disk drive? Not at all. I mean, anybody who thought that doesn't understand the purpose of the interface. The colors are not supposed to represent the true colors of files because files don't have colors. The shapes aren't supposed to represent the true shapes because files don't have shapes. And the positions don't represent true positions. So the whole point of the interface is not to tell you the truth, it's to hide the truth, right? You don't want to know about the diodes, the resistors, the megabytes of software, the voltages, the magnetic fields. If you had to know all that, you could not write your program, edit your image, whatever. You couldn't, write your email. So the whole point of the interface, it's useful because it hides the truth and it gives you a dumbed down, pretty guide to behavior. It's guiding your behaviors so that you can get done what you need to do. And that's the idea about perception. The idea about perception then from the interface is that space and time that we perceive are a species-specific desktop. Space and time is our desktop, and what we call physical objects are the icons on our desktop. And to ask if they're the truth or not is the same mistake as asking if is the file really blue and really rectangular. It's just the wrong question. Our perceptions did not evolve to even deal with truth. They're there to hide the truth. So what we call the physical world has been evolved by natural selection actually to hide the truth and just guide adaptive behavior.
What is the context of truth that you were using?
What is the context of truth I was using? The nice thing about being the creator of a computer program is you get to play God. So you can say, this is the world, and you write down a mathematical structure. And then you say that the perceptions of the organism are exactly isomorphic to the mathematical structure of that world. So you can actually say, let it be so, and it is. So the interface theory says that space-time is not the truth. What we call the physical world is not the truth. It's not intended to be the truth. We've evolved not to see the truth, but to hide the truth. It's too complicated. The truth is too complicated. We don't need to know it. Space-time is our desktop. Physical objects, like this podium, are just the icons of that desktop. Now, the obvious question then to me, in many cases, is, well, Hoffman, if you think that train coming down the tracks at 200 miles an hour is just an icon of your desktop, why don't you step in front of it? And after you're dead and your theory with you, we'll know that the train was real. And the answer is, I wouldn't step in front of the train for the same reason I wouldn't drag that file icon to the trash carelessly. Not because I take the icon literally, the file's not blue, but I do take it seriously. If I drag that icon to the trash, I could lose a year of work. The same thing with the train icon. I don't take it literally, it's just an icon. But I've been shaped by evolution to have symbols that, although they're not true, I need to take seriously. If I don't, I'll go extinct. And those of our ancestors who didn't, they're not here. They weren't our ancestors, actually. The desktop then gives us a fiction of causality. We think that when one object hits another, a billiard ball hits another one, that it causes it to move. Well, that's just a useful fiction on the desktop. If I drag the icon to the trash can, it looks like the movement of the icon to the trash can caused it to delete the file. That's a nice fiction of causality, but in fact, it's just a fiction. And so causality in physical space is also a fiction. And that then raises, now we move into the consciousness side. If our perceptions of what we call the physical world are just a useful fiction, and there's no causality in that physical world, that then means we have to rethink the mind-body problem. The standard view is that physical properties such as neural activity of the brain causes consciousness. But if this interface theory is correct, then no physical object has any causal powers, and that includes the brain. The brain causes none of my perceptions, it causes none of my actions. It's a nice symbol. It's a dumbed-down symbol. It seems complicated to us, but it's the dumbed-down symbol that we use when we look inside of heads. So, I've been working to develop a theory of consciousness. I mean, I do want a science of consciousness, where I recognize that a scientific description of consciousness is not consciousness, just like a scientific description of the weather is not weather. You don't need to put on your rain suit when you run a simulation of the weather. And you don't need to put on, worry that consciousness will emerge from a scientific theory. But nevertheless, as a scientist, I want to try to get a mathematical model of consciousness that's precise so that I can be precisely wrong. That's the whole point of science, is to be precise enough so that people can say, here's why you're wrong, and then you can try to fix it. So that's my goal. So here's the idea. The idea about consciousness, and I'm going to define something called a conscious agent, is there is the world, where I won't specify what the world is right now. The world somehow leads rise to my conscious experiences, qualia and other conscious experiences. Those then, I make decisions about how I'm going to act. Based on what I perceive, I make decisions about what actions I will take, and those actions then go back and affect the world. So there's this closed loop. That's the basic idea. So now you turn it into mathematics. W stands for the world. X stands for the conscious experiences of the agent, and G is for the potential actions. You might say, why not A? I'll use that in a moment. So G is for something called groups. So now there's going to be a map from the world to my conscious experiences. I'll call that P. There's just some kind of mapping. Then the conscious agent will have to make a decision. So there'll be some mapping D, which in some sense expresses the free will choices of the conscious agent. And then the action that you take then is a mapping that changes the state of the world. And every time you have a conscious experience, we have a counter that says +1. Another conscious experience, another one. So you're counting the conscious experiences. So you have a counter, right? So my definition, a conscious agent is these 7 items: W, X, G, the world, experience, my set of actions; P, the perceptual map; D, my decision map, which is my conscious will; A, my actions, my action map, which changes the world; and N, which is my counter of experiences. So a conscious agent is mathematically a 7-tuple, so there it is, where, now here's the math. I'll assume that W, X, and G are so-called probability spaces, so that I can talk about the probability of having this experience or that. So it's the most general assumption that allows me to talk about the probability of making a certain decision, decision G, having an experience X, and changing the world W. The maps that I talked about, the P, the perception, decision, action maps, are all going to be Markovian kernels. That's the most general formalism that allows me to have probabilistic changes from one to the other, to map the world probabilistically onto my experiences. For those of you who know information theory and communication theory, these Markovian kernels are in fact identical to communication channels. So you can think of each one as a communication channel. If you know linear algebra, each of these is just a matrix whose rows sum to 1. So that's the mathematical content of it, for those who know that stuff. And N is an integer, right? You're just counting up the number of experiences that you have. So it's not that difficult a mathematical structure. And then, now here's where part of going out on a limb, making risky claims, I claim what I call the conscious agent thesis, that every conscious entity and every conscious activity can be modeled by interacting conscious agents. That's the claim. It's in a similar spirit to the Church-Turing thesis in the theory of computation. Turing proposed this formalism called the Turing machine and made the claim that every effective procedure can be written as an instance of this abstract formalism that he wrote down. And it turns out that was the foundation of computer science. That allowed all sorts of important theorems and proofs to be made about computer science, and it's a falsifiable hypothesis. If you could find an effective procedure that couldn't be instantiated as a Turing machine, that would falsify his hypothesis, but it's not really provable. So I'm proposing this thesis in the same spirit as the Church-Turing thesis. I'm proposing this is the formalism that handles all of consciousness. If you find a counterexample, I'm wrong. But quite that simple. So the conscious realism thesis then says, what is the world? Because there's that world W, right, in the definition of the agent. And by the way, that's where the theory is non-dual, because the world is actually in the definition of the conscious agent itself, is not separate. So the conscious realism thesis says that the world W itself consists of conscious agents. So the whole game is consciousness. That's the proposal. So these are very clean, falsifiable hypotheses. So we can talk about two conscious agents, 1 and 2, and here I've written their structures. So the world, the perceptual map, the experiences, the decision map, the actions, and then the action map, and the experience counter for each agent. Why is there more than one agent? Well, ultimately, we're going to be looking at a dynamics of interactions of agents, but it's going to turn out that under many circumstances, when two agents interact, it becomes a theorem of this mathematics that a new single agent appears. So the nice thing about the mathematics is it makes precise mathematical predictions about consciousness and about when self-awareness actually comes out, and I'll show you at top level what that is. So I'm going to take these two agents, and the conscious realism thesis says that the W has to be conscious agent. So I'm going to make, in this particular example, the world for agent 1 be agent 2, and vice versa. So I'm going to take agent 1, I'm going to open them up a little bit, right? And I'm going to plug in to W another agent. This is conscious realism now, mathematically realized.
So each agent is perceiving the same
Other agents. No, each agent is perceiving other agents, and you might be, the nexus of agents that you're interacting with will determine the kinds of perceptions you have. Also, your space X and G will be different from agent to agent. So we can have a wide range of different agents, right? X, it could be the conscious experiences of you, and it could represent the experiences of a bat. So very, very widely different conscious experiences. You can think of X, for example, as being, when the agent's not perceiving at all, it's the potentiality of conscious experiences. It's consciousness with silence, no content. But when this thing actually interacts, then you get the content. So the mathematics actually allows us to talk about consciousness without content, the silent consciousness. So here I have two conscious agents now interacting, and you can see the direction of the arrows. Information is flowing in a cycle around this, and the experience counters keep going around as they interact. The compatibility condition is that, for this to happen, is that the actions of one equal the perceptions of the other. So you have a mathematical compatibility constraint for them to interact. You can write this abstractly too. You can just think of two conscious agents, C1 and C2. One is sending messages. So here's a sender, here's a receiver, receiver, and the information is cycling between them. You have conscious experiences happening here, free will decisions. So this is the consciousness as will, and then consciousness as action. So consciousness is conscious experience, free will, and then free action. You can put three of them together. I'm simplifying. I showed you two, but there's a complete combinatorics. You can put any number of these together. That's one way to put three together. Here's another way to put three together. Have them all interacting. You can put four together. So all of a sudden you get very interesting lattices of arbitrary complexity of interacting conscious agents. Now the mathematics says, there's a theorem, that whenever two connected conscious agents occur, when actually two agents are connected, a new conscious agent is thereby instantiated. A new single conscious agent emerges. And it's what I call the introspecting conscious agent. So you have the two agents that are interacting with each other, and the new single agent can sort of be described this way. It has its receiver, here's its receiver, the experiences that it's getting. This is its free will decision, that's the sender. I can show it on this. So the receiver, the conscious experiences, the free will choices, and then the actions, which are the senders. And what this agent is doing is, it is its own world. It is perceiving itself, so this is introspection. So the mathematics of this theory says that as soon as you have two agents interacting, the mathematics says there will be conscious introspection. It's just part of the theorem. So that means introspection is far more ubiquitous than perhaps we thought. Now I'll give you a concrete example of the kinds of dynamics that can happen. As you can see, it's infinitely complicated, right? The agents here have enough structure. They're in terms of computation power, they're universal. Anything that you want to compute can be computed with these things. And any architecture you want can be instantiated with them. So it's a very, very powerful framework. But I'm going to give you one trivial example. This is the experiences of the one agent, and it can only experience what I'll call 0 and 1, like red and green. That's all it can experience. These are the only actions it can take, 0 and 1. This is the experiences of the other agent, 0 and 1. Say it can see blue and green. That's all it can see. And these are the only actions it can take. And then these arrows indicate some simple probabilities. This agent, if it experiences green, it sends out action 0. If it sees red, it sends out action 1. These are then just transported without change around this architecture. In this particular example, you could have these things crossing. You could have these be non-trivial probabilities. I'm showing you one example out of an infinity just to be concrete. So I hope you see what's happening is this is the conscious experiences, these are the actions, and these arrows, these are experiences, these are actions, and the arrows are the perceptual and action and decision maps that I was talking about. Now the question is, how do we relate this theory of consciousness to what we call the physical world? Because if we want to solve the mind-body problem, and we're starting with consciousness, then my constraint is I have to get physics from my theory of consciousness. Otherwise, again, I'm falsified. If I cannot derive all of physics from just this basic thesis of the definition of conscious agents and conscious realism, so one definition and one postulate, that's all I'm starting with, my burden is then to get all of quantum field theory and eventually quantum gravity from just this foundation. If I can't do it, I'm wrong. So that's, it's very, very clear. So I'm just going to show you at top level the connections that I've already made and the connections I'm hoping to make. Whenever you have a dynamics like this, it turns out that there is going to be cyclic behavior. And in this particular case, the cycles are a state. This says 0, 0, 0, 0. The first thing over here is 0, 0, 0, 0. What I'm saying is, suppose I start off these two agents where this agent is seeing 0, its action is 0, this one is seeing 0, and that action is 0. Suppose that's how we start off the dynamics. And now we start letting the arrows act on that dynamics. What's going to happen? Well, at the next step, when n goes to the next step, right, you increment your experience counter, you'll go to 0, 1, 0, 0. So this will still be a 0. This will now be a 1, because see, 0 goes to 1, right? But the rest of them will still be zeros. And if you actually work through it, you'll see that you go through 0, 0, 0, 1, 0, 0, 0, 1, 1, 0, and so forth, all the way back to 1, 0, 0, 0, and then you back to where you started, 0, 0, 0, 0. So you cycle through 8 states in this particularly simple example, right? Very, very simple, just to illustrate the point. So you get a cycle through 8 states. And then there's another one. If you start off with 0, 0, 0, 1, you get a different cycle of 8 states, okay? So those are called absorbing sets, and it turns out that in the theory of Markov chains, because these are Markov chains, you can actually characterize this so-called long-term behavior, asymptotic behavior of the system in terms of the eigenfunctions. So the states are the 0, 0, 0, 0, 1, 0, 0, and so forth. Those are the states S. D is the cycle period. In this particular case, 8, because you went through 8 different states to get back to where you were. N is the step time, 1, 2, 3, so forth. And it turns out that the mathematical description that falls out from the theory of conscious agents now, so this is the mathematical description of the long-term behavior that comes from just the mathematics of conscious agents, is this weird equation here. Pretty nasty, but notice that it involves an imaginary number, e to the I, times cis theta is, the CIS is cosine theta minus I sine theta. 5? Okay. So this says how the long-term behavior of the agents maps out mathematically. Here is the wave function of the quantum free particle. They're mathematically identical. In fact, let's put them close together. What you can see is that the position x of the particle corresponds to the state S of the dynamics of the conscious agents. The time t for the particle corresponds to the experience counter of the agents. The period d of the agents corresponds to the both the central time period and the wavelength of the particle, and that the speed of light is in units of 1. That the momentum is actually Planck's constant over the d, the period of the conscious agents, and that the energy is Planck's constant times c, which are both 1 in these units, divided by d, the period of the conscious agent dynamics. So in other words, from the asymptotic, the idea then is that physical particles are identical to asymptotic behaviors of the dynamics of conscious agents. That's the connection. Asymptotic dynamics of conscious agents are what we represent in our little space-time interface as particles. And that allows us to read off a solution to the mind-body problem in terms of how states of the dynamics are equivalent to physical properties of the particles. So I'm going to do a couple claims and replies and then just hint where I'm going with this. So one claim about consciousness and science is that consciousness can't be measured or observed. I would claim rather that consciousness, if what I've been saying is correct, consciousness is the only thing that science has ever observed. Claim and reply, consciousness is subjective and private, physical objects are objective and public. And if you look at this very, very carefully, it turns out that there are no public physical objects. A spoon, or this podium, is no more public than your headache. We can both talk about headaches and communicate because we've both had them, but there's no public headache. In the same way, we can both talk about the podium that we're each creating as perceptual experiences, but there's no public podium because podiums aren't part of objective reality. There's no scientifically testable theory of consciousness. Conscious agents are such a theory. It's a falsifiable theory. Finally, qualia, conscious experiences, can't be scientifically studied or mathematically described. Yes, they can. This is done by the field of psychophysics, which is a field that I'm involved in. That's where a lot of this mathematics came from, was the study of psychophysics and the math models that we've gotten there. So just in the last minute, I'll just say where I'm going. This is the speculative part. The connection that I showed you is between conscious agents, asymptotic dynamics, and non-relativistic physics. The equation I gave you was for non-relativistic particles. Of course, you need to go to a relativistic situation, and for that I'll just sketch. This is at the edges of what I'm doing, so I hope I'm not wrong. Two agents interacting. There are 4 variables that are involved. There's the N1, N2, the experience counters, X1 and X2, which are the experiences themselves, the state of the experiences, and G1 and G2, which are the choices of actions for the 2 agents. So, and it turns out when you look at this, that you can write down what's called a geometric algebra, G of 2, 4, where the N1 and N2 have positive signature in the algebra, and the other variables, X's and G's, have negative signature. And this is the geometric algebra of conformal spacetime. So this is the conformal spacetime algebra. It turns out that this is the algebra that's used in relativistic descriptions of particles. For example, Dirac spinors fall right out of this, and Penrose's twisters. So my next direction is to actually show that when you have 2 agents like this, that their dynamics actually forms the base of the massless relativistic particle description in physics at the Planck scale. And then the idea is that mass comes in later as a symmetry breaking, where the symmetry breaking is you have other agents that then start to communicate with these 2 agents. So the 2 agents that are just interacting, that's the symmetry. When another agent starts to interact with them, you have a symmetry breaking, and that's where mass comes in and different scales of time. This is all speculative, and thank you very much. Okay.